All right, so we're working on box 7C here, intersection of a line and a plane. And if we have a line and a plane in space, so we're working in 3 dimensions here, because obviously if we have a line and a plane in 2 dimensions, then we just have one possible plane, and so the line has to be in the plane. So we're working in 3-dimensional lines, and of course planes only really make sense in 3 dimensions. So there are 3 possibilities, and these possibilities should be kind of familiar to you by now. We can have the line and the plane being parallel and distinct. So the plane, we're representing it by this nice little pink oval here, but remember it stretches off to infinity in all directions. And of course our line extends to infinity in all directions. Our line can be parallel to our plane, in which case these 2 things are not going to intersect. So parallel and distinct, no intersection. Or we can have the situation where the line actually lies inside of the plane, in which case this is sort of corresponds to the situation when we were working with 2 lines, where our 2 lines were coincident. Okay? So if the line lies in the plane, every point on the line is a point of intersection between the line and the plane. And we've drawn one here that kind of goes like this. Of course, we could have a line that goes like this, or a line that goes like this, or whatever. As long as those lines are contained within the plane, there's going to be an infinite number of points of intersection. So the new one, I guess the most interesting ones is, and I guess the most common one as well, is that they intersect at a single point. So this line, which extends off to infinity, punches through this plane at some point in time. And you get this situation, number 3, anytime your line and your plane are not parallel to each other. So again, checking to see if these things are parallel is going to be pretty important here. So let's just jump right into an example here where we want to find the intersection for these 2 things that were given here. Now, one of these things is a line, one of these things is a plane. Which one is which? And how do you know? Okay, this is our plane over here. You can tell this is a scalar equation here. You can tell it's not a line because we've got a z here, which means we have to be working in 3 dimensions. And if we're working in 3 dimensions, we can't have the Cartesian equation of a line in 3 dimensions. We could only have the Cartesian equation in 2 dimensions. So this little z in here tells us that we're working in 3D. So this has to be the equation of a plane. How do we know this other thing over here is a line? I'll just call it L2. How do we know that this isn't the equation of a plane? Yeah, so it only has 1 parameter and 1 direction vector. So this has to be the equation of a line. So the first thing we want to check is, are these 2 things parallel? Are plane 1 and line 2 parallel? And the way that we can check this is by, well, looking at the vectors that we can easily get from our equation for a plane and our equation for a line. From our plane, we can get our normal vector. We'll call this normal 1 here. The normal vector is going to be 2, 3, -4. It's just those coefficients a, b, and c in our Cartesian equation. And from our line, we can easily get our direction vector. Direction vector here is going to be -1, -2, -2. How can we check to see if these 2, how can we check using these 2 vectors to see whether these things are parallel or not? Well, remember, the normal goes perpendicular to the plane. So this is at sort of right angles to our plane. Okay? If our line is going to be parallel to the plane, then our normal here also has to be perpendicular to that direction vector. So the question we want to ask is, n1 also perpendicular to this direction vector? And by now, you're sick of checking to see if vectors are perpendicular to each other. All we need to check here is the dot product. If the dot product equals 0, these two things are perpendicular. So we're going to do that normal dotted with that direction vector, which is going to give us 2, 3, -4, dotted with -1, -2, -2, and we can work out what this is. -2 minus 6 plus 8. So this does, in fact, equal 0. Okay. So what does this tell us? Okay. Dot product is 0, so we can conclude that the normal is perpendicular to our direction vector, which means our line and our plane are parallel to each other. Therefore, plane 1 and this line that we've called line 2 are parallel. So they're either parallel and distinct, or the line is in the plane. How can we check to see if this line is inside of the plane? Yeah, we can check, let's say, what are we checking for here? We're checking if they are coincident. So, no, sorry, I shouldn't say coincident. I should say, is L2 in the plane 1? And we're going to do this by checking a point from L2 in the equation that we have for that plane. So it's nice that we have the vector equation for that line 2, because that gives us a point right away. So that point that we have is 4, 2, 5. And we're going to check it by subbing it into that scalar equation, or that Cartesian equation that we have for plane 1. So what do we get when we do this? Let's just do a left side, right side check here. So we'll have our left side is going to be 2 times 4 plus 3 times 2 minus 4 times 5, and we can work out what this is. This all works out to 8 plus 6 minus 20, which is not -14, but 14 minus 20, which is -6. And our right side, we look back up, our right side was -7. Okay. So what does this tell us? Left side does not equal right side, so we can conclude that this point, 4, 2, 5, is not in the plane. So what can we conclude about our line and our plane? Well, we already know that they're parallel. Because this point doesn't check out for us, they are, we can say the plane and the line are what? Yeah. Parallel and distinct. Okay. So again, just like when we were working with two lines, check to see if things are parallel first, because that's going to determine where you go with the rest of the question. So let's take a look at another example here. Find the intersection for these two things that we have here. We've got 4x minus 2y plus z equals 19. And this thing that I've written in a slightly different form than you might have seen before. This guy over here is our plane. We'll call that plane 1. And this one is the equation of our line. And I'm going to rewrite it in the form that we're familiar with just by bringing these numbers that appear on the left-hand side over onto the right-hand side. So this is going to become 3 minus 3 minus 3 plus t times 232. Okay? It's a more familiar vector equation. All right. So first step, are these guys parallel? Our normal vector is 4, negative 2, 1. Our direction vector, again, we'll call this line 2. Our direction vector from 2 is 2, 3, 2. We're going to do the dot product of these two things. It's going to get us an expression that looks like this, which is going to be, if we work this all out, we end up with 4. So we can emphatically say, no, these things are not parallel. So once we know that they are not parallel, we need to find the point of intersection. And there has to be a point of intersection if they are not parallel. So let's look at how we actually find the coordinates of that point of intersection. I think the easiest thing to work with is, this is like step 1 here, we will find the parametric equation of our line. Of this line that we're working with. So we've got our vector equation there. Let's just change that into parametric form. So we'll have x equals 3 plus 2t, y equals negative 3 plus 3t, and our z is going to be negative 3 plus 2t. Okay. So this gives us expressions for x, y, and z. Now, if our line is intersecting our plane, there is a point where these two things intersect. At that point, we have coordinates, or values for x, y, and z, that satisfy both this equation and the equation that I have up here. So what we can do is we can take these expressions that we have for x, y, and z and sub them into the equation of a plane for x, y, and z. So that's step 2. Sub into the equation for the plane. Sub into scalar equation of the plane. Equation of the plane. So when we do that, what do we end up with? Well, we'll have 4 times 3 plus 2t minus 2 times negative 3 plus 3t plus negative 3 plus 2t, and all of this is going to be equal to 19. So now we have an expression in terms of t. So we want to solve this thing for t. So let's expand. 12 plus 8t plus 6 minus 6t minus 3 plus 2t equals 19. Collect our like terms here to get 15 plus 4t equals 19. So 4t is going to equal 4, and t equals 1. So how does this help us? Well, this is the value of t for which the x, y, and z values that we get from the parametric equation satisfy the scalar equation of the plane. What we want to end up with is coordinates x, y, and z for that point of intersection. So we just need to use this value of t in our parametric equations. So use t in our parametric equations to get x, y, and z. So what were our parametric equations? Well, let's see. X is going to be 3 plus 2 times 1, so we'll have an x value of 5. Y is going to be negative 3 plus 3 times 1, which is going to give us 0. And z is going to be negative 3 plus 2 times 1, which gives us negative 1. So we've got our values of x, y, and z, and they represent the point of intersection. So therefore, our plane and our line intersect at the point 5, 0, negative 1.